Something is amiss in our expanding cosmos. Nearly a century ago, astronomer Edwin Hubble discovered the balloon-like inflation of the universe and the accelerating rush of all galaxies away from each other. Following that expansion backward in time led to our current best understanding of how everything began, the Big Bang. However, over the past decade, an alarming hole has been growing in this picture. Depending on where astronomers look, the rate of the universe's expansion, a value called the Hubble constant, varies significantly. Now, more than 2 years after its launch, the James Webb Space Telescope has cemented this discrepancy with stunningly precise new observations that threaten to upend the standard model of cosmology. According to Adam Rees, a professor of astronomy at Johns Hopkins University who led the team behind these measurements, it's a disagreement that has to make us wonder if we really do understand the composition of the universe and the physics of the universe. Many cosmologists agree that the universe began with a bang. In an instant, the young cosmos formed as an expanding, roiling plasma broth of matter and antimatter particles, which popped into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma should have consumed each other entirely. However, scientists believe an unknown imbalance enabled more matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed pockets of plasma, squeezing and heating the matter, and sound waves traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surfaces. Meanwhile, the high energy density of the early universe's crowded contents stretched spacetime, pulling a small fraction of this matter safely from the fray. As the universe inflated like a balloon, ordinary matter, which interacts with light, congealed around clumps of invisible dark matter to create the first galaxies connected by a vast cosmic web. Initially, as the universe's contents spread out, its energy density, and therefore its expansion rate, decreased. Roughly 5 billion years ago, however, galaxies began to recede from one another at an ever faster rate. The cause of this acceleration was attributed to another invisible and mysterious entity known as dark energy. The simplest and most popular explanation for dark energy is that it is a cosmological constant, an inflationary energy that remains uniform across time and space. Einstein named it lambda in his theory of general relativity. As the cosmos grew, its overall matter density dropped while the dark energy density remained unchanged, gradually making the latter the dominant force driving the universe's expansion. The combined energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's expansion. These components are also key ingredients in the lambda cold dark matter, CDM, model of cosmology, which maps the universe's growth and predicts its eventual end, with matter spread so thin it results in a heat death called the Big Freeze. While many predictions of the CDM model have proven highly accurate, significant challenges remain. Despite extensive efforts, astronomers have no clear understanding of dark matter or dark energy. According to Ofer Lohov, a professor of astronomy at University College London who was involved in galaxy surveys of dark energy, most people agree that the universe's present composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing fact is we don't understand the last two of them. An even greater threat to the CDM model has emerged. Depending on the method used, the universe appears to be expanding at different rates. This disparity, known as the Hubble tension, reveals that methods examining the early universe show it expanding significantly faster than CDM predicts. These methods, vetted and verified by countless observations, suggest a possible flaw in the model itself. As Rees explains, the only reason that I can understand at this point for them to disagree is that the model that we have between them is perhaps missing something. Measuring the universe's expansion requires more than a radar gun. One method relies on the cosmic microwave background, CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. This imprint, seen across the entire sky, was mapped by the European Space Agency's Planck satellite between 2009 and 2013 to determine the Hubble constant with less than 1% uncertainty. In this cosmic baby picture, the universe appears almost entirely uniform, but hotter and colder patches, where matter is denser or less dense, reveal where baryon acoustic oscillations cause matter to clump together. As the universe exploded outward, its structure ballooned into a vast cosmic web, resembling a network of interconnected strands. These strands became the intersections where galaxies would eventually form. By analyzing ripples in this cosmic structure using the Planck satellite, cosmologists inferred the quantities of regular matter, dark matter, and the cosmological constant, also known as dark energy. Incorporating these values into the standard model produced a Hubble constant of approximately 67 km per second per megaparsec. A megaparsec equals 3.26 million light-years, and this number has profound implications. For instance, a galaxy 1 megaparsec away from us recedes at 67 km per second. At a distance of 20 megaparsecs, this recession velocity grows to 1,340 km per second, continuing to increase exponentially. Beyond a distance of 4,475 megaparsecs, galaxies move away faster than the speed of light. A second method to determine the universe's expansion rate involves studying pulsating stars known as Cepheid variables. These are dying stars with outer helium gas layers that periodically expand and contract, causing their brightness to flicker rhythmically, like distant signal lamps. In 1912, astronomer Henrietta Swan-Leavitt discovered that brighter Cepheids flickered more slowly. This relationship allowed astronomers to measure a star's absolute brightness and estimate its distance, revolutionizing astronomy. Cepheids became reliable standard candles for gauging the universe's immense scale. By connecting observations of pulsating Cepheids, astronomers built cosmic distance ladders, each rung extending their view further into the past. This technique remains one of the most precise tools available for measuring cosmic distances. Wendy Friedman, an astrophysicist at the University of Chicago, explained that constructing a distance ladder begins by measuring the distances to nearby Cepheids using both their pulsating light and geometric methods. Subsequent rungs rely solely on Cepheid observations. Astronomers then compare the distances to stars and supernovae on these rungs, correlating how much their light has been redshifted, stretched to longer, redder wavelengths by the universe's expansion. This process yields an accurate measurement of the Hubble constant. In 2019, Adam Rees and his collaborators used this method, employing the Hubble Space Telescope to study Cepheids in the Large Magellanic Cloud, one of the Milky Way's closest neighbors. Their results indicated an unexpectedly high expansion rate of 74 km per second per megaparsec, which conflicted with the Planck measurement. However, Hubble's limited precision in crowded star regions caused distant Cepheids to blur into neighboring stars, leaving room for dissenting cosmologists to suggest measurement errors. The launch of the James Webb Space Telescope in December 2021 aimed to resolve this discrepancy. With a 6.5-meter wide mirror, nearly 3 times the size of Hubble's 2.4-meter mirror, Webb can detect objects 100 times fainter and is far more sensitive in the infrared spectrum, enabling broader wavelength observations. Comparing Cepheids measured by Webb in the galaxy NGC 4258 with Type Ia supernovae, another standard candle known for their consistent luminosity, Rees and his team arrived at a nearly identical expansion rate of 73 km per second per megaparsec. Independent results using the Hubble Space Telescope, focusing on the bright tips of red giant branch stars, and another study analyzing gravitational lensing of light by massive galaxies, produced respective values of 69.6 and 66.6 km per second per megaparsec. A separate gravitational lensing study also yielded 73 km per second per megaparsec, leaving cosmologists puzzled. According to Ryan Keeley, a cosmologist at the University of California, said, the discrepancy between measurements is statistically significant. The cosmic microwave background, CMB, temperature is measured with 1% precision, and the Cepheid distance ladder is approaching similar precision. A difference of 7 km per second between the methods, while small, is unlikely to be random. This has led to an unresolved tension, dividing cosmologists into factions pursuing vastly different explanations. An attempt to address the issue at a 2019 conference at the Kavli Institute for Theoretical Physics in California only heightened the debate. David Gross, a Nobel laureate and former director of the institute, described the situation as a crisis rather than a mere problem. Resolving the discrepancy remains challenging. Rees has proposed a modification to the CDM model, suggesting that dark energy might not be constant but could evolve over time due to unknown physics. However, Keeley's research contradicts this, showing that expansion rates align with CDM predictions back to the CMB. If adjustments to the model are necessary, they likely pertain to the universe's earliest moments. One possibility is the presence of additional dark energy before the emergence of the CMB, providing extra impetus to the universe's expansion without contradicting the standard model. Another group of astronomers believes that the tension, coupled with the observation that the Milky Way resides inside an underdense supervoid, suggests that lambda-cold dark matter, CDM, and dark matter must be discarded altogether. According to Pavel Krupa, a professor of astrophysics at the University of Bonn, what should replace it is a theory called modified Newtonian dynamics, MOND. This theory proposes that for gravitational forces 10 trillion times smaller than those experienced on Earth's surface, such as the weak pulls felt between distant galaxies, Newton's laws break down and must be replaced by alternative equations. Some astronomers, however, argue that their calculations contradict the claims made by MOND. Despite this, Krupa insists that cosmologists attempting to adjust the standard cosmological model are merely adding complexity to an already convoluted theory. From Krupa's perspective, what is being observed represents a fundamental breakdown in science itself. A more optimistic view suggests that the standard model may simply require some adjustments. Alternatively, dark matter and dark energy could be modern-day equivalents of epicycles, the small circles ancient Greek astronomers used to model planetary orbits around Earth. These epicycles fit the data well until the heliocentric model placed the Sun at the center of the solar system, rendering them obsolete. Krupa speculates that this could be the current situation, although it is also possible that dark matter and dark energy exist but have yet to be discovered. To resolve these mysteries, cosmologists are exploring various approaches. Cosmic microwave background, CMB, experiments, such as the CMB-S4 project in Antarctica and the Simons Observatory in Chile, are conducting ultra-precise measurements of radiation from the early universe. Others are relying on dark matter maps from the European Space Agency's Euclid Space Telescope or data from future dark energy surveys conducted by the Dark Energy Spectroscopic Instrument. While it seems increasingly unlikely, the Hubble tension might still be resolved by uncovering some unseen systematic error within current measurements. For scientists like Wendy Friedman, the solution, or potentially more questions, could come from the James Webb Space Telescope. Friedman's team is using its powerful observational capabilities to study Cepheid variables, tip of the red giant branch stars, and carbon-rich JAGB stars to measure distances with unprecedented accuracy. Once the data is collected, it may provide clarity on whether systematic issues exist, potentially settling the long-standing debate. Until then, astronomers can only hope that this day arrives soon. Despite our extensive knowledge of the universe, countless mysteries remain unsolved, and scientists are eagerly working to uncover them. Among these mysteries is the question of how supermassive black holes merge. When black holes collide, they produce gravitational waves that ripple through space. However, the mergers observed so far involve stellar mass black holes, each just a few tens of times the Sun's mass, minuscule compared to supermassive black holes, which can have billions of solar masses. Supermassive black holes reside at the centers of major galaxies, and when galaxies collide, the black holes should, in theory, merge. Yet a problem arises. As these black holes spiral inward, they lose energy through interactions with surrounding gas, dust, and stars. But when they are within a parsec of each other, there's no longer sufficient material to shed energy, leaving them in a stalemate. This final parsec problem suggests that supermassive black holes should remain in orbit and never actually merge. However, data from the NANO Grave experiment indicates that the universe emits a background hum of gravitational waves, likely from supermassive black hole mergers. This hum could provide essential clues to solve the mystery. Another profound question concerns the universe's large-scale structure. Observations reveal galaxies strung along filaments forming a vast cosmic web. These structures appear to have originated from tiny density variations in the early universe, which grew into the massive superclusters and voids we observe today. Yet, the Big Bang theory posits that the early universe should have been nearly perfectly smooth. How did these minuscule imperfections, with variations of just a few parts in 100,000, lead to the formation of such grand structures? These are the pressing issues occupying the finest astronomical minds, with the James Webb Space Telescope expected to shed new light on the mysteries of our vast universe. One explanation for the Big Bang is a modification called inflation, which describes what happened in the first few seconds of the universe. It proposes that the universe underwent a period of superrapid expansion during the first minuscule fraction of a second, growing from a size much smaller than an atom to approximately the size of a grapefruit in a trillionth of a trillionth of a trillionth of a second. Before this, the universe was so small that it was dominated by minute quantum variations. The subsequent explosion in size amplified those variations. It is worth noting that, while inflation helps address certain issues with the Big Bang theory, there is currently no direct evidence that it actually occurred. Additionally, the true size of the universe remains unknown. Astronomers typically refer to the observable universe, a spherical region extending 13.8 billion light-years in all directions, which represents the area where light has had enough time to reach us since the Big Bang. However, beyond this cosmic horizon, there could exist regions so distant that their light has not yet reached Earth, making it challenging to determine the universe's overall shape. Astronomers currently believe that the four-dimensional fabric of spacetime is flat, although it is possible that inflation has smoothed out the regions we can observe, while the universe beyond could be curved. Another mystery about the universe concerns the true nature of gravity. While we understand its effects, how gravity functions remains unclear. Einstein's general theory of relativity, our best explanation, describes gravity as the warping of spacetime caused by massive objects, such as the Sun. Earth, for example, is caught in the Sun's distortion, which explains its orbit. However, this approach differs from how physicists understand the other three fundamental forces, which are mediated by particles known as bosons. For instance, magnets attract each other by exchanging photons. Physicists are searching for the graviton, a hypothetical particle that might explain how gravity works. The enigmatic nature of black holes is another pressing question. One common query is what happens if someone falls into a black hole. Approaching too closely to the event horizon would result in extreme gravitational differences between a person's head and feet, effectively stretching them into a state often described as spaghettification. But what happens to this spaghetti? According to Einstein's general relativity, space inside a black hole becomes increasingly compressed, culminating in an infinitely small point known as a singularity. However, this concept likely represents a gap in our understanding, as the laws of physics fail to predict what occurs when space curvature and density become infinite. Quantum physics, which governs the behavior of matter at incredibly small scales, could offer insights, but physicists have yet to reconcile it with general relativity. A unified theory of everything may one day replace the singularity with a more accurate explanation. Another significant unknown is the nature of dark matter. Galaxies rotate at such speeds that their outer stars should be flung into space, yet they remain bound. This suggests the presence of an invisible gravitational force called dark matter, which holds galaxies together. But the composition of dark matter remains elusive. For decades, scientists have theorized that it consists of weakly interacting massive particles, WIMPs. However, exhaustive searches for these particles have yielded no results, prompting consideration of other possibilities. These include primordial black holes formed shortly after the Big Bang or particles known as actions, hypothesized to resolve certain issues in particle physics. Some theories even suggest that dark matter might not be a physical substance but an illusion caused by gravity behaving differently on a galactic scale, as proposed by the modified Newtonian dynamics (MOND) theory. The formation of galaxies is another fascinating puzzle. The modern universe contains hundreds of billions, perhaps trillions, of galaxies, but their origins remain a topic of debate. Two main scenarios are proposed. In the bottom-up approach, individual stars and small star clusters formed first, with gravity, aided by dark matter, gradually combining them into galaxies. Alternatively, the top-down approach suggests that massive structures formed early in the universe's history and fragmented into galaxies as time progressed. Observations from the James Webb Space Telescope have revealed fully formed galaxies existing just 400 million years after the Big Bang, and some in the process of merging, lending support to the bottom-up model. However, the reality might not be so clear-cut, as both processes could have contributed to the galaxies we see today. It may be possible for some galaxies to form from the bottom up, while others formed from the top down. Huge upcoming galaxy surveys, such as those conducted with the Vero Rubin Observatory in Chile, could provide crucial insights into this process. Additionally, the James Webb Space Telescope is only just beginning its mission, promising groundbreaking discoveries. Astronomers used to believe that the gravity of everything in the universe would eventually cause the cosmos to collapse back in on itself, in an event termed the Big Crunch, a reversal of the Big Bang. However, this notion changed with the discovery that the universe's expansion is accelerating due to a mysterious force known as dark energy. If this acceleration continues, all structures in the universe, even atoms, could be torn apart within 22 billion years in a phenomenon called the Big Rip. Alternatively, a more gradual expansion could lead to a big freeze, where the universe cools so much that stars cease to shine, and it ultimately settles into a uniform, cold state. The ongoing advancements in telescopic technology promise to unveil unprecedented wonders of the cosmos. Over the past 3 decades, the Hubble Space Telescope revolutionized our understanding of the universe. Now, the James Webb Space Telescope represents a significant leap forward with its infrared vision, larger mirror, advanced sunshield, focus on the early universe, and enhanced exoplanet studies. By providing an unparalleled depth of data in record time, the James Webb Space Telescope is rewriting the textbooks of cosmology. Its observations are breaking new ground and challenging existing records, offering profound insights into the cosmos. Telescopes like the James Webb Space Telescope are often compared to time machines. When they observe distant objects, they are simultaneously looking back in time due to the finite speed of light, which travels in a vacuum at approximately /3.0 times 10 to the power of 8 text, ms. This constant speed, often referred to as c, means that light takes time to travel across space. For everyday objects, such as a neighbor's cat, the delay between light leaving the object and reaching our eyes is negligible. However, for astronomical distances, the time delay becomes significant. For instance, light from the Sun, which is about 93 million miles, 150 million kilometers, from Earth, takes approximately 8 minutes and 20 seconds to reach us. If the Sun were to suddenly blink out, we would only notice the change after this delay. Similarly, an observer on Uranus, nearly 20 times farther from the Sun than Earth, would experience a delay of about 2 hours and 40 minutes. The significance of light travel time grows when we consider the universe's vast scale. Instruments like the James Webb Space Telescope, the Atacama Large Millimeter Array, and the Hubble Space Telescope allow astronomers to observe light that originated millions or billions of years ago, revealing objects as they appeared in the distant past. As light traverses the expanding universe, its wavelengths stretch to longer, redder wavelengths, a phenomenon known as redshift. Measuring this redshift helps astronomers calculate the distance of celestial objects. The higher the redshift, the farther away the object is, and astronomers have long been racing to identify the most distant galaxies. With its exceptional infrared capabilities, the James Webb Space Telescope is perfectly suited for detecting these longer wavelengths. Positioned 1 million miles from Earth, it has dramatically redefined our understanding of high redshift galaxies, or high-Z objects. In 2015, the most distant galaxy observed had a redshift value of about 8, but subsequent discoveries by the Hubble Space Telescope pushed this to redshift 11. Now, the James Webb Space Telescope has shattered these records, moving the redshift frontier to values of 14, corresponding to a time approximately 13.5 billion years ago, when the universe was less than 300 million years old. These remarkable galaxies were first identified during a deep space survey conducted with Webb's near-infrared camera, one of its primary instruments, in a region of the southern sky known as the Jade's Origin Field. This area, about a quarter of the size of a full moon, revealed 11 galaxies dating back to when the universe was less than 400 million years old, far more than scientists initially expected. However, these galaxies' extreme redshifts are not their most intriguing feature. Researchers believe that several other candidates awaiting confirmation may have even higher redshifts, potentially providing a glimpse into even earlier moments in the universe's history. The galaxies captured by the James Webb Space Telescope are remarkable for their exceptional brightness, size, and color, characteristics closely linked to their population of stars. These features contradict the Big Bang theory, the prevailing explanation for the universe's origin and evolution. According to this theory, early galaxies should generally be small and dim due to their relative youth, lacking the time to accumulate mass and stars. However, the galaxies observed by Webb defy these expectations, appearing as radiant blobs containing masses hundreds of millions of times that of our Sun. Some theories suggest this brightness might stem from supermassive black holes at their centers, but the concentrated light typical of such phenomena is absent. Instead, scientists propose that these young galaxies have somehow already produced nearly 500 million stars, with their actual stellar productivity potentially even higher. The peculiar color of these galaxies offers additional clues. Normally, young galaxies are very blue due to the prevalence of short-lived, high-mass stars that shine brightly before dying. However, Webb's observations reveal massive galaxies that are surprisingly red. This redness could be due to galactic dust, which forms when stars expel material or die, scattering light and making it appear redder. This effect is similar to how dust in Earth's atmosphere turns sunsets red and orange. Webb's mid-infrared measurements and the detection of ionized oxygen clouds, an element forged in stars, further support the presence of dust. However, this explanation raises a perplexing question: how could a galaxy so young already host multiple generations of stars, producing enough dust to obscure its light? Detecting oxygen in such a young galaxy is akin to finding an ancient city equipped with modern technology like iPhones, challenging our understanding of cosmic timelines. In light of these discoveries, scientists are considering whether something fundamental about our understanding of the universe might be incorrect. The Standard Model of Cosmology, a cornerstone of modern astrophysics, has been a triumph of human ingenuity. Originating from Edwin Hubble's discovery in the 1920s that the universe is expanding, it gained further support in 1964 with the discovery of the cosmic microwave background, a remnant of the early universe's hot, dense state. Over decades, cosmology has become increasingly precise, accounting for data with remarkable accuracy. However, this precision has relied on the existence of unobservable components like dark matter and dark energy, which are said to constitute 27% and 68% of the universe, respectively, with only 4% being normal, visible matter. The model also incorporates theories like cosmic inflation, which posits that the universe expanded exponentially for a fraction of a second after the Big Bang. While this solves certain problems, it introduces others, including the idea of a multiverse, an infinite number of universes, most of which are fundamentally unobservable. Although indirect evidence often supports such theoretical components, Webb's data on galaxy formation, coupled with issues like the Hubble constant discrepancy, casts doubt on whether the model remains viable. A familiar narrative about scientific progress often reassures us in moments like this. When confronted with data that challenge existing theories, researchers refine their models to better align with evidence, embodying both humility and triumph. This process might unfold here as well. Cosmologists may propose a new, dark, phenomenon to reconcile Webb's findings with the Standard Model. However, the challenges posed by these observations could also signal the need for a deeper conceptual revolution, fundamentally altering our understanding of the universe and its most basic features. There is another possibility to consider. We may be at a point where a radical departure from the Standard Model is needed, one that may even require us to rethink how we understand the elemental components of the universe, possibly even the very nature of space and time. After all, the discovery of Webb's impossibly massive early galaxies is raising all sorts of new questions and theories. This is the kind of exciting anomaly researchers had hoped the James Webb Space Telescope would uncover. Scientists agree that Webb's capabilities have not yet been fully realized, and none would be surprised if the telescope sets a new redshift record within the year. In short, thanks to the James Webb Telescope, we are witnessing the extraordinary diversity of galaxies that existed at cosmic dawn, and the scientific community is eager to explore these fascinating weirdos. In addition to uncovering the secrets of the cosmic dawn, the James Webb Space Telescope is now helping us better understand how planets form. For a species that developed on the life-giving planet Earth, it remains astonishing that we lack a complete scientific picture of how planets form in the universe. Even with advanced observatories like NASA's Hubble, we've only managed to capture snapshots of stellar systems at different ages and stages. However, the advent of the infrared-sensitive James Webb Telescope and the powerful radio capabilities of ALMA have allowed us, for the first time, to piece together a more comprehensive picture of planetary formation. This progress has profound implications for our understanding of our own solar system. The most complete story of planetary formation assembled to date might seem unlikely. Every star, as far as we know, begins its life as a cloud of gas. These gas clouds are typically massive and warm, with enough kinetic energy to counteract their gravitational potential energy, preventing collapse. Over time, however, heat radiates away due to the presence of heavy elements and molecules, diminishing the kinetic energy and leading to a scenario where the gas cloud undergoes fragmentation and gravitational collapse. This process takes place over a relatively short span, ranging from a few million to a few 100 million years, and occurs in various regions within the cloud. Each collapsing region may contain as little as 1 or 2 solar masses or as much as tens of millions of solar masses. Stars can form in isolation, small groups, or clusters with hundreds to millions of newborn stars. Within each stellar system, an initially asymmetric clump of matter contracts into a dense core, where one or more stars will form. Surrounding this core is a two-dimensional disk of material that connects to the central core. However, a paradox exists in star formation. For gas to gravitationally collapse, it must cool, but for nuclear fusion to ignite within a star's core, the temperature must be extremely high, around 4 million Kelvin. Remarkably, gravitational collapse provides a simple astrophysical solution to this dilemma. As the gas cloud collapses, its volume and surface area decrease, making it harder for heat to radiate away. This trapped heat, a result of adiabatic contraction, raises the temperature of the central protostar while its density increases. Once the core temperature surpasses the critical threshold, nuclear fusion ignites, marking the star's birth. At this stage, the radiation and pressure emitted by the star increase dramatically. Initially, the circumstellar disk remains fully attached to the star, allowing matter to accrete onto the protostar. The star's emitted particles and photons are insufficient to halt its continued growth, while the surrounding disk remains undifferentiated, hot, and featureless. This phase typically lasts between 500,000 and 2 million years. Eventually, a protoplanetary body becomes large enough to create features like spiral patterns, gaps, or rings within the disk. A gap also forms between the young star and the disk, separating them and enabling planet formation. The inner edge of this gap often lies well within the soot line, close enough to the star that even heavy chemical compounds are broken down by its energy and emitted particles. The emergence of gaps and features within the circumstellar disk marks the end of its undifferentiated phase. These circumstellar disks, also known as protoplanetary disks, regions where planets begin to form. Once the central star ignites, the material within the disk is thrust into a race against time, as the majority of the gas is blown away by the star's radiation within just a few million years. Initial imperfections within the disk grow through gravitational attraction, drawing matter from both their orbits and surrounding regions. These imperfections evolve into protoplanets and eventually mature into full-fledged planets, provided they survive gravitational encounters with other forming objects vying for dominance. During this chaotic period, interactions are frequent. Small planetesimals collide, sometimes merging to form larger bodies and other times breaking apart. Young planets and protoplanets interact gravitationally, leading to outcomes such as merging, ejection, or collision with the central star. The largest early planets dominate their surroundings, accreting material and perturbing the orbits of smaller objects. This process often destroys lower mass worlds, preventing them from becoming stable planets. Despite the initial turbulence, a more stable planetary system begins to emerge over time. After approximately 10 million years, the gas-to-solid mass ratio in the system decreases significantly, dropping from an initial ratio of 100 to 1 or higher to around 1 to 1. This shift indicates that the major planets within the stellar system have largely taken shape. In our solar system, it is assumed that the 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, along with potentially additional large planets, formed during this early phase. Jupiter was likely much closer to the Sun initially. The original planetary configuration of the inner solar system may have been disrupted by Jupiter, resulting in planets being absorbed, ejected, or hurled into the Sun. As gas levels declined, Jupiter's outward migration created opportunities for smaller bodies to form and survive in the inner solar system, eventually giving rise to Mercury, Venus, Earth, and Mars. Planet formation transitions to a different stage rather than ending abruptly as the gas dissipates. When the initial gas of the circumstellar disk is nearly gone, planet formation is considered complete. For decades, this model represented the prevailing understanding of planet formation and remains largely accurate for massive planets throughout the universe. However, the material left in young planetary systems includes gas, young planets, planetesimals, and solid bodies at various distances from the star. These include objects at frost lines, where compounds transition between solid and ice states, and numerous solid bodies in outer regions resembling the Kuiper belt. This stage is characterized by heavy bombardment of planetary bodies by comet-like and asteroid-like objects, as well as potential giant collisions. The late heavy bombardment, a phase in our solar system's history lasting until about 700 million years after the Sun's formation, is evidenced on surfaces like the Moon, Mercury, and Mars. Despite its name, this period did not involve a sudden spike in bombardment rates but rather marked the tapering off of an extended period of extreme collisions. Around 3.8 billion years ago, the rate of violent events subsided, coinciding with the earliest signs of life on Earth. During this time, significant collisions shaped the system. Approximately 50 million years after the circumstellar disk phase ended, a massive impact between young Earth and the protoplanet Theia gave rise to the Moon. Mars experienced a similar event, leading to its moons Phobos, Deimos, and a third now destroyed moon. Pluto underwent a collision that formed its five-moon system, while Triton, once the largest Kuiper belt object, was captured by Neptune. These events marked the transition to the debris disk phase, where the system stabilized and bombardment waned. Like humans growing through phases from infancy to adulthood, stellar and planetary systems also undergo distinct stages. During the protostar and undifferentiated circumstellar disk phase, planets are not yet formed, and the seeds of planetary bodies are as easily destroyed as they are created. As the circumstellar disk differentiates, planetesimals emerge as the seeds of planets, growing rapidly like gestating fetuses. However, many are devoured, ejected, or drawn into the star. Once the disk evolves into a debris disk, these baby planets experience a turbulent childhood and adolescence, marked by violent episodes that shape their formation. Moons around rocky planets form during this phase, and some smaller planetesimals persist to become planets, like Mercury and Mars. When the debris clears, a process that can take hundreds of millions to nearly a billion years, the surviving planets are mature. From this point onward, gravitational interactions are rare, and the system remains relatively stable for billions of years. In mid-2024, we stand at a remarkable juncture in understanding the formation and evolution of planetary systems. While many details about how planetary systems form and mature remain to be investigated, we have now assembled the most comprehensive and detail-rich picture of planetary formation to date. This story acknowledges significant deviations in very high-mass and very low-mass stellar systems and recognizes considerable variation among individual systems, much like the diversity observed within human populations in terms of height, weight, or other characteristics. For the first time, however, astronomers can craft a detailed narrative of planetary evolution, thanks to a wealth of data previously unavailable before the advent of groundbreaking observatories like ALMA and the James Webb Space Telescope. This evolving story of planetary formation begins with matter transitioning from a uniform, undifferentiated disk around a protostar to a nearly gas-free system containing mature planets orbiting one or more stars in a stable fashion. The transition from a circumstellar disk to a debris disk phase, along with the persistence of debris disks over long periods, remains poorly understood. Future observations of young planetary systems are expected to address these knowledge gaps. Nevertheless, the framework for planetary formation across the universe now aligns consistently with the history of our own solar system, marking a significant milestone in astronomical understanding. Simultaneously, the James Webb Space Telescope is transforming our understanding of the cosmos, shedding new light on the universe's 14 billion-year history. Since its launch in December 2021, this remarkable observatory has exceeded expectations, uncovering an abundance of bright galaxies from the universe's earliest epochs. These findings challenge existing models of galaxy formation, as the observed brightness, indicative of star numbers and mass, suggests galaxies far more massive than anticipated for such an early cosmic stage. This revelation raises profound questions about the fundamental principles of cosmology, including whether the universe's age or the very concept of its origin needs re-evaluation. Astronomers grappling with James Webb's discoveries have likened the challenge to encountering unusually large toddlers in a foreign land, prompting a reassessment of growth theories. The unexpected mass and maturity of these early galaxies, observed in the universe's first 500 million years, challenged the long-held belief that galaxies gradually coalesce over billions of years. Instead, the data suggests galaxies formed and evolved far more rapidly than previously understood, necessitating revisions to our theories of galaxy formation and evolution. The James Webb Space Telescope has become an indispensable tool for investigating these mysteries. Designed to peer back in time, it leverages the principle that light, traveling at a finite speed, takes longer to reach us from distant objects. This enables astronomers to observe events that occurred billions of years ago. The telescope's sensitivity to infrared light, which travels greater distances with minimal loss of brightness, allows it to capture detailed images of the farthest objects in the universe. By doing so, James Webb provides a view of the cosmos as it existed in its earliest stages. Recent observations have revealed unprecedented details about early galaxies, such as GZ9P3, one of the earliest known galaxies identified by the telescope's international collaboration. With a redshift of Z equals 9.3, this galaxy offers a glimpse into the universe's infancy. The telescope's advanced capabilities have thus not only validated existing theories but also introduced new paradigms in our understanding of galaxy formation, bridging the gap between science fiction and reality in the quest to unravel the mysteries of the universe. A few years ago, GZ9P3 appeared as a single point of light through the Hubble Space Telescope. However, observations with the James Webb Space Telescope revealed this object as it was 510 million years after the Big Bang, approximately 13 billion years ago. The findings showed that, like other early galaxies observed by James Webb, GZ9P3 is significantly more massive and mature than expected for a galaxy from the infant universe. During this ancient period, it already contained several billion stars. This discovery presents a cosmic conundrum. How did early galaxies like GZ9P3 grow so massive so quickly? Remarkably, it is about 10 times more massive than other galaxies observed by James Webb during similar epochs. Kit Boyett, a team member and scientist at the University of Melbourne, noted that GZ9P3's size and maturity are not its only remarkable features, its shape provides further clues to its creation. Using direct imaging with James Webb, researchers identified that GZ9P3 has a complex structure with two bright patches, indicative of two dense nuclei. This suggests GZ9P3 likely formed through the collision of two early galaxies. This merger may still have been ongoing when astronomers observed GZ9P3 with the James Webb Space Telescope. As Boyett explained, the galaxy's morphology resembles that of two interacting galaxies, and the merger appears incomplete because two distinct components remain visible. Such collisions cause massive objects to eject matter, and this discarded material observed in GZ9P3 represents one of the most distant mergers ever recorded. In addition to studying its age, mass, and shape, researchers delved into the stellar population within GZ9P3. Young stars, being brighter than older ones, dominate images of distant galaxies whose light has traveled billions of years to Earth. For example, a young population sparked by the galaxy's merger, less than a few million years old, outshines an older population already over 100 million years old. The research team overcame this challenge by employing spectroscopic observations and direct imaging. Spectroscopy revealed the chemical composition of stars, enabling the researchers to differentiate between young and old stars. Older stars, having depleted the hydrogen in their cores, fuse helium into heavier elements known as metals. Thus, older stars are richer in metals compared to their younger counterparts, which are primarily composed of hydrogen and helium. Using James Webb, the team identified specific elements in the older stellar population of GZ9P3, including silicon, carbon, and iron, the latter being the heaviest element stars can synthesize. When these stars exploded as supernovae, they enriched the early universe with metals, which later became the building blocks for new generations of stars. Notably, the population of old stars in GZ9P3 was much larger than previously anticipated. This finding indicates that galaxies may have achieved chemical maturity faster than expected. The observations suggest a rapid and efficient buildup of stars and metals in the aftermath of the Big Bang, closely tied to ongoing galaxy mergers. Galaxies isolated from their counterparts form stars slowly and stop when they deplete their reservoirs of gas and dust. However, galaxies in close proximity can experience a revival of star formation when they collide. These mergers trigger an inflow of fresh gas, initiating periods of rapid star formation known as starbursts. Such events are instrumental in the rapid growth of stellar populations, as demonstrated by GZ9P3. Most large galaxies, including our own Milky Way, have grown through mergers. The Milky Way, for instance, has cannibalized smaller satellite galaxies and currently forms stars at a slow rate. However, this rate is expected to increase when it collides with the Andromeda Galaxy in approximately 4.5 billion years, triggering a fresh starburst. Observations of GZ9P3 underscore the significant role of mergers in the early universe's rapid mass accumulation and star formation. Boyd remarked that these findings reveal galaxies in the early universe accumulated mass through mergers with higher star formation efficiencies than previously believed. These and other observations from the James Webb Space Telescope are prompting astrophysicists to rethink their models of the universe's early years. While our overarching cosmology remains intact, the understanding of how quickly galaxies formed needs revision, as early galaxies appear far more massive than once thought. A collection of ancient galaxies could have transformed the entire universe. While the James Webb Space Telescope has created more and more puzzles, it has also solved many others with its new observations. The James Webb Space Telescope recently revealed a collection of ancient galaxies that packed a massive punch, shaping the universe when it was less than 1 billion years old. An international team discovered galaxies resembling today's dwarf galaxies, which played a vital role during a crucial stage of cosmic evolution between 500 and 900 million years after the Big Bang. These small galaxies vastly outnumbered larger galaxies in the infant universe. Scientists say it is likely that these galaxies supplied most of the energy needed for a process called cosmic reionization. Cosmic reionization was critical for the growth and progression of the universe, as Hakim Atek, research lead author and an astronomer at the Institut Astrophysique de Paris, said, "We're really talking about the global transformation of the entire universe." The main surprise is that these small, faint galaxies had so much power, their cumulative radiation could transform the entire universe before about 380 million years after the Big Bang, during a period known as the Epoch of Recombination. At that time, the now 13.8 billion-year-old universe had been opaque and dark. This was because, in its dense and ultra-hot state, free electrons endlessly bounced around particles of light called photons. However, during the Epoch of Recombination, the universe expanded and cooled enough for electrons to bond with protons and form the first atoms of hydrogen, the lightest and simplest element in the cosmos. The disappearance of free electrons meant photons were suddenly free to travel, and as a result, the dark age of the universe ended. The cosmos became transparent to light, and this first light can still be seen today in the form of a cosmic fossil called the cosmic microwave background, CMB. Because electrons and protons have equal but opposite electric charges, these first atoms were electrically neutral, but they would soon undergo another transformation. After 400 million years, the first stars and galaxies formed, and during the era of reionization, neutral hydrogen, the predominant element in the universe, was transformed into charged particles, known as ions. Ionization happens when electrons absorb photons, gaining enough energy to break free from atoms. Until now, scientists were uncertain about the source of the ionizing radiation behind reionization. Possible sources had included supermassive black holes feeding on gas from surrounding accretion disks, ejecting high-energy radiation, and large galaxies with masses in excess of 1 billion suns, as well as smaller galaxies. Identifying smaller dwarf galaxies as the main sources of ionizing radiation was a challenge for a long time due to their faintness. Fortunately, the Webb telescope's infrared spectroscopic capabilities allowed it to observe them. One of the reasons for building this observatory was to understand what happened during the epoch of reionization. However, even with the Webb telescope's impressive infrared observing power, detecting these dwarf galaxies would not have been possible without the help of Albert Einstein. More specifically, his 1915 theory of general relativity, which predicts how light behaves when passing near massive objects. General relativity suggests that all objects with mass warp spacetime, the combined entity of space and time. This curvature of spacetime causes our perception of gravity and leads to the bending of light. The greater the mass of an object, the more extreme the curvature, which in turn increases the strength of its gravitational effects. This curvature not only affects the movement of planets and stars but also alters the paths of light coming from background sources. As light passes close to massive objects, it can take different paths, and the closer it is to such an object, the more it is bent. As a result, light from the same object may arrive at Earth at different times. This bending of light is known as gravitational lensing, and it allows the James Webb Space Telescope to observe ancient galaxies near the dawn of time, which would otherwise have been impossible to see. To analyze the light emitted by distant and early dwarf galaxies, Webb used a galaxy cluster called Able 2744 as a gravitational lens. With the mystery of reionization potentially solved, the team plans to extend their study on a larger scale with another Webb project called Glimpse. They will first aim to confirm whether the location studied in this research is representative of the average distribution of galaxies in the universe. Beyond studying reionization, they aim to better understand the formation of the very first galaxies, which over the course of 12 billion years grew into present-day galaxies. Evidence for the first generation of stars has emerged, thanks to observations made by the James Webb Space Telescope. This proof was found in one of the most distant galaxies known, GN-Z11, which was discovered by the Hubble Space Telescope in 2015. Prior to the launch of the James Webb Space Telescope, GN-Z11 was considered the most distant galaxy known, with a redshift of 10.6. Rather than discussing how far away this galaxy is, it's more accurate to talk about how long ago it existed. It is because we see GN-Z11 as it was just 430 million years after the Big Bang, due to the time it took for its light to travel to our corner of the cosmos. For comparison, the universe today is 13.8 billion years old. As such, GN-Z11 was a prime target for the James Webb Space Telescope to study. Two new papers now describe profound discoveries about GN-Z11, revealing vital details about how galaxies that existed in the early universe were able to grow. GN-Z11 is the most luminous galaxy known at this particular redshift, and indeed, this has become a common theme for high redshift galaxies, which are now almost regularly being found in the early universe by the James Webb Space Telescope. Many of these galaxies appear much brighter than what our models of galaxy formation predict they should be, with these predictions based on the standard model of cosmology. Now, Webb's new observations seem to have shed light on what is going on. An astronomy team led by Roberto Molino of the University of Cambridge has probed GN-Z11 with Webb's two near-infrared instruments, NIRCam and NIRSpec. The researchers discovered evidence for the first generation of stars, known as population 3 stars, as well as for a supermassive black hole that is gobbling up huge amounts of matter and growing at a vastly accelerated rate. Scientists can calculate the age of a star based on its abundance of heavy elements, which would have been formed by previous generations of stars that lived and died, spewing those heavy elements into space where they ultimately get recycled in star-forming regions to form new stellar bodies. The youngest stars that have formed in the past 5 or 6 billion years are referred to as population 1 stars and have the highest abundance of heavy elements. Our Sun is a population 1 star. Older stars contain fewer heavy elements because there had been fewer generations of stars before them, and these are called population 2 stars, which live in the oldest regions of our Milky Way galaxy. However, population 3 stars had been purely hypothetical until now. These would have been the first stars to form, and because no other stars came before them, they would have contained no heavy elements, being made only from the pristine hydrogen and helium forged during the Big Bang. These first stars are also thought to have been extremely luminous, with masses equal to at least several hundred suns. Although astronomers still haven't seen population 3 stars directly, Molino's team detected indirect evidence for them in GN-Z11. NIRSpec observed a clump of ionized helium near the edge of GN-Z11. This helium gas is being ionized by something that's producing huge amounts of ultraviolet light, with that something inferred to be the population 3 stars. The helium witnessed may be leftover material from those stars' formation. The amount of ultraviolet light required to ionize all that gas would require about 600,000 solar masses of stars in total, shining with a combined luminosity 20 trillion times brighter than our Sun. These figures suggest that distant galaxies, such as GN-Z11, would have been more adept at forming massive stars than galaxies in the modern universe. Meanwhile, according to a second set of results, Molino's team also found evidence for a 2 million solar mass black hole at the heart of GN-Z11. Specifically, they found extremely dense gas, which is common in the vicinity of supermassive black holes accreting gas. These were the first clear signatures that GN-Z11 is hosting a black hole that is actively gobbling matter. The team also detected a powerful stream of radiation flowing off the accretion disk of matter swirling around the black hole, as well as ionized chemical elements typically found near accreting black holes. This marks the discovery of the most distant supermassive black hole so far, the team reports, and its gluttonous appetite leads to its accretion disk becoming dense and hot, shining brightly. This, combined with the population 3 stars, is what makes GN-Z11 shine so brightly. The researchers believe this does not break standard cosmology, as some have prematurely claimed, but rather presents an extremely red supermassive black hole growing in the early universe. Elsewhere, using the James Webb Space Telescope, astronomers have discovered an extremely red supermassive black hole growing in the shadowy early universe. The red hue of this black hole, observed as it was around 700 million years after the Big Bang, is the result of the expanding universe. As the universe balloons outward in all directions, light traveling toward us gets redshifted, and in this case, the redshifted light indicates a cloak of thick gas and dust shrouding the black hole. Examining Webb's data, the astronomy team, led by Lucas Ferak and Adi Zitrin of Ben-Gurion University of the Negev, was also able to determine the mass of the supermassive black hole to be around 40 million times the mass of the Sun. This mass is unexpectedly large in comparison to the galaxy in which it resides. The team also found that the supermassive black hole, located around 12.9 billion light-years away from Earth, is rapidly feasting on the gas and dust surrounding it. In other words, it's growing, as Ferak said in a statement. 3 very compact yet red-blooming objects prominently stood out and caught our attention. Their red dot appearance immediately led us to suspect that they were quasar-like objects. Quasars are created when large amounts of matter surround supermassive black holes. This matter forms a disk of gas and dust, called an accretion disk, which gradually feeds the black hole. The immense gravitational influence of the black hole churns this matter, generating intense temperatures and causing it to glow. Additionally, matter that doesn't fall into the supermassive black hole is channeled to the cosmic titan's poles. Particles in these regions are accelerated to speeds approaching the speed of light, creating highly accelerated jets. As these relativistic jets are blasted out, the eruptions are accompanied by bright electromagnetic emissions. As a result of these phenomena, quasars powered by supermassive black holes in active galactic nuclei are often so bright that the light they emit outshines the combined light of every star in the galaxy that surrounds them. The vast amount of radiation being emitted from around this particular supermassive black hole caused it to take on a small, point-like appearance in the Webb's data. Analysis of the object's colors indicated that it was not a typical star-forming galaxy, further supporting the supermassive black hole hypothesis. Together with its compact size, it became evident that this was likely a supermassive black hole, although still different from other quasars found during those early times. However, it's important to note that the early quasar wouldn't have been visible, even to the powerful infrared eye of James Webb, without a little help from an effect predicted by Albert Einstein in 1915. In this case, the Webb telescope used a galaxy cluster called Abell 2744 as a foreground lensing body to amplify light from background galaxies that are otherwise too distant to see. This revealed the extremely red quasar they zeroed in on originally, which appeared as 3 red dots. Further analysis of the background source revealed that its light must have come from a compact region. According to team member and Princeton University researcher Jenny Green, all the light of that galaxy must fit within a tiny region the size of a present-day star cluster. The gravitational lensing magnification of the source gave them exquisite limits on the size. Even if they packed all the possible stars into such a small region, the black hole ends up being at least 1% of the total mass of the system. This discovery adds to the mystery of how supermassive black holes, which can be millions or even billions of times as massive as the Sun, grew to such huge sizes during the universe's infancy. As we are told, James Webb has detected a wealth of little red dots over time. These could indicate feeding supermassive black hole-powered quasars in the early universe, potentially meaning that the striking black hole growth conundrum could soon be solved. In a way, it's the astrophysical equivalent of the chicken and egg problem. We do not currently know which came first, the galaxy or the black hole. How massive the first black holes were and how they grew are questions still unanswered. That's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. Be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.